So happy Thursday. Welcome back to class, live from my basement. It's not a hotel room, it just looks like that because it's a guest room that I took over. So we have, let's see, example 3B on tap for today, and then lecture 4 probably getting started. You have a formative assessment you can be working on. So we'll have that due on Monday, and the TAs will lead that discussion the following day. And another one back to back, and then we'll have a homework. And that one is not available yet, and I will let you know once it is. How's that sound? All right, can someone say hello so I can check the recording?
Hello.
There we go, it's on. I think it's gonna work. All right, excellent. So we are talking about kinds of ANOVAs, right? So they all have in common what things? I'm watching the chat, or you can talk to me, your call.
They don't allow missing data.
They do not if they're using least squares estimation. That is a thing. So those things are often tied together, method of estimation and model choice. The models per se don't have a stipulation that they can't have missing data, but least squares estimation does. So when people say ANOVA, they're usually talking about least squares, so I will take it. Requiring balanced data, yeah. Time is categorical. Yep, those two ideas are together. Time is treated as a categorical predictor, which means you have to have discrete versions of it. So that means balanced data in terms of everyone being on the same potential schedule. Let's see. Anything else we can think of they have in common? Model for the means is saturated, yes. So we are estimating as many fixed effects as we have occasions. One intercept, which will be the reference occasion, and then dummy codes essentially differentiating each other occasion from that reference as if time is a grouping variable. Can't have random slopes. Yeah, I think that's more of a software thing than like a technically possible thing, but you wouldn't find those in there. And no time varying predictors for the same reason. It's not built into this, and the software doesn't anticipate that. Good. Any other things you want to review or talk about before we jump into example 3B? Okay, cool. Well, then here we go. So I warned you that you're going to see a lot of this data set this semester. I'm going to use it for example 6, which is actually 4 separate handouts. At one point they were all together for example 6, and then it got to like 80 pages, and I was like, okay, this is ridiculous. So we split them up. But this one is only a mere 8 pages, so very, very doable, especially from our Zoom session here. So we have, these are real data. I talked about this last time in answering a question about how to separate effects of practice from effects of real change. But just to reiterate, these are real data from real older adults who lived in assisted living. And the purpose of the study was to examine individual differences and the extent to which they improve in a speeded task. So this is a cognitive test called number match 3 is what we call it. There is a row of 3 digits and then a second row of 3 digits, and as quickly as possible you have to say whether the digits are the same or different. So it's an easy task, but it's a speeded task, and improvements in response time as measured in milliseconds is what we're going to be looking for. So this is an interesting example because the point is change, right? This is a study that was designed so that we could see people improve in this task over time, but it's not measuring age-related change or any kind of cognitive decline because all of these 6 sessions of practice are happening over a 2-week period. So in terms of the metric of time, what we're going to keep track of is which session it is, how practiced they are, as opposed to whether it was 1 day later or 2 days later or whether it was Tuesday or what have you. So we're not expecting time to be meaningful per se. It's exposure to the test is what we're tracking. And I think that fits in a lot of other real world applications as well. So we have 101 older adults. They range in age from 64-ish, I think, up into their 80s. And we're going to be fitting the 3 kinds of ANOVAs to these data and paying attention to how our inferences about how the means differ over time depends on what's in our variance model. So there's 3 possibilities. This data set is already in long format. So that is 1 row per occasion per person. So each person has 6 rows of data in this data set. So all I had to do was import it. And R made me do a couple extra things within this. In order to get the output to look correct, it wanted me to sort it by person and time to begin with. And I'm like, all right, that seems like a reasonable thing to do. Just descriptive statistics. So these are observed means. In this case, because I have complete data, the observed means in the data set are going to match the means that the model recreates when I fit the saturated means model. That will not happen if you have missing data. So that's one of the things that gets tricky in reporting longitudinal analyses, is that typically in a methods section, you would have tables of descriptive statistics, right? You'd have means and standard deviations and sample sizes. And those are perfectly reasonable things for people to want to know about. However, the observed means is not what the model is going to try to recreate. It's going to try to recreate the means as estimated using some kind of likelihood, which is means that would be what they would have been had the data been complete under an assumption of missing at random. So the two will diverge to the extent that you have a lot of missingness, in particular missingness for reasons. Like if you have dropout, then the folks who drop out probably are not randomly selecting themselves to drop out, right? There's reasons. So just keep that in mind, that the observed means in the descriptives will not necessarily match the outputted means from your model. The latter is really what the trajectories we're going to fit are going to try to recreate, the model estimated means as opposed to observed. But these are observed. This is data output from Summarize. And here's a picture of the means. So the y-axis here is cheated, by the way, that's my word for it. It's 1400 to 2200 milliseconds. I would not normally plot a y-axis that narrowly because I think it makes the story look a little bit grander than it is, but I wanted to focus on the shape of the change indicated by these means. So what is happening over time for these folks? Are they getting better or worse? We'll start with some softballs. Yeah, this is response time. So they're getting better. Yeah, they're getting faster. I once had a professor tell us, like, he had this very strong opinion in talking about response time. Like, you can't say like longer or shorter, it has to be faster or slower. And I don't remember like his rationale, but I know he had very strong opinions about that. I do not. So faster, can we say that? They're getting faster? Yeah, the mean response time is getting lower. Foreshadowing, the rest of Unit 6 here, do you think they're improving at the same rate over time? Really. In most learning trials, you see a curve that looks like this, where right away there's a much greater rate of improvement and it kind of diminishes as they go on here. So we will explore a bunch of different types of functions that would try to approximate this kind of bendy line. Bendy is my generic term for some kind of nonlinearity. So those are the means. What about the standard deviations? Do you see any patterns or trends across those? We start at like 550, then 510, 483, 466, 460, 443. They're going down too. So what is happening in this data set is that people are getting more homogeneous the later they are in the study. Practice effects are sort of leveling the playing field. They start out more disparate at the beginning than they have later on. So this pattern, when you see standard deviations changing in like in a constant way like this is a dead giveaway that we have individual differences in change. The only way that you would have variances that are the same over time is if people change all the same and the trajectories are parallel. Then they will stay equally spread out across time. So that is my my indication that we will need some kind of model that allows individual differences in change. So that one is coming up later. I wanted to show you the options that ANOVA gives us for right now. Did the same thing in R. Okay, let me close this thingy here. There we go. So this is my equation for the predicted response time at time t for individual I. So t is level 1, I is level 2. And in R and Stata, the default for categorical variables when you let the model do the dummy coding for you is to make the first group the reference. So I set it up that way. So beta 0 is going to become the mean at the first occasion, session 1, and then S2 through S6, these would be binary indicators for whether it's that occasion is a 1, and if not, it's a 0. So these act like switches, essentially. So how many fixed effects are in this model for the means? More softballs? How many betas are in there? Six. You're like, is this a trick? It's not a trick. This is me shamelessly encouraging the participation portion of the program, even though we're on Zoom. 6. How many occasions do we have? 6. So that's what saturated means, is that we have as many fixed effects, 5 slopes and an intercept, as we have occasions. That's going to perfectly reproduce the 6 means. So this is, on the model for the mean side, this is the answer key to what any fixed effects of time would be trying to reproduce, these 6 means. And I don't have any variance parameters on here because that's the part that's going to change across the handout, is what is the model for the variance that goes with this thing. So the first option is what we call a straw man, meaning we know it's not going to work, but we put it up as a point of comparison. Between person or between groups standard ANOVA. Now, why do I say this isn't going to work? Why don't I think this is going to work for longitudinal data very well? What's in a between groups ANOVA in terms of their model for the variance? Feel free to read from the screen. Yeah, only sigma, yep, only E, residual variance, and no random intercept. Yep, so that implies that occasions are independent, as it is called in Stata. So I took pity on y'all this time and I was like, pay attention to this part. The part in yellow is what makes this different. Everything else is the same. So Stata calls this independent, and this part of it technically is not necessary, but what this is the ID variable for which session is which. In further models, if you have missing data, you put the ID in so that makes sure that your R matrix is structured properly. Otherwise, like if I had occasions 1, 2, and 6, and I didn't tell it this, it would try to put occasion 6 in row 3 instead of row 6 of the variance covariance matrix. So this makes sure that everything goes into the right spot if you have missing data across people. So here's my output in terms of fixed effects. That thing is my fixed intercept. So session 1, I have the option turned on to tell it what the reference group is. That is called base level. I learned about that recently. Session 1 is the reference. 1961 milliseconds is what they take on average to do this task the first time they try it. So almost 2 seconds to make a correct answer. And then the rest of these are mean differences relative to session 1 specifically. So relative to session 1, session 2 is lower by 146. Relative to session 1, session 3 is lower by 211, and so forth. And I have these things labeled out here as to what the parameters are. So this is not as useful as it could be. Like this one piece of information tells me all about how session 1 compares to each of the others, but logically I'd like to know about all of the differences, as well as whether on the whole there's an overall difference. So can you think of a way that you already know to ask the question, like, are these means the same or are they different as a set? Are these mean differences? Are the means the same according to this? How do we lump stuff together to test it? Yep, omnibus F-test is what we would call that in ANOVA language. We're talking about whether there's a main effect of time, essentially. Because there are 6 possibilities, that's 5 degrees of freedom. And so we can ask for that. That is not a default in Stata, but I know how to get it. So margins are the actual means implied by this model, and I showed you out here the math by which that happens. So if I take beta 0 as the intercept, and I add to it beta 1 for how the second occasion differs, the result is right here. So that's how the model is parameterized. Even though the first occasion is the reference, the rest of the model tells you what each of the other occasions means has to be as a linear combination. And the nice part about treating session as categorical in the program, the I dot here, it makes it really convenient to get all the possibilities. You don't have to write them all out as lincoms or other kinds of statements like that. So margins for the win. What about the standard errors for these things? Same or different across time? Same because model assumes same. Yeah, exactly right. This model says there is a residual variance that holds across time. Coincidentally, it predicts the same amount of error around each of these point estimate means because the variance is expected to be the same over time. In the data, we saw that that wasn't the case, though. So that's why I say this may not fit very well. Mean differences. That's another thing that if you're doing the coding of the binary indicators yourself that you would have to do. But if the program does it for you, then this is yet another quick way to get all the pieces of information that you want. So I also wrote out the logic by which these other mean differences are computed. So the ones that deal with session 1 as the reference are all directly model parameters. Like that's what the dummy codes mean. The ones that are amongst the alternatives are linear combinations of those. So the way that I wrote this is, for instance, 3 versus 2. We look at that one right there. The mean for session 3 is created as beta 0 plus beta 2. The mean for session 2 is created as beta 0 plus beta 1. So if you do the math to figure out what the mean difference would be, the intercept drops out, and you're left with beta 2 minus beta 1 as how the model tells you what that mean difference is supposed to be. And you can do it for all of the other combinations, which I did there. I did not do any alpha correction on this. I don't really worry about that kind of stuff too often, but if that's something that matters to you, then you can ask for modified p-values that take into account all of these different comparisons. The reason I don't worry about it so much is, to me, it's completely arbitrary which of these mean differences show up as model parameters and which are implied by the model. Like, so I don't view it as separate to like, oh, I need to worry about these tests, but not those ones. It's too arbitrary for me. Why is there DF600 in the code? That was for degrees of freedom. According to this model, I have 600 independent observations, actually 606, so minus 6 for the ones that I spent. I estimated 1 variance and 5 mean differences. That's my 6 parameters. Contrast is how you ask for the omnibus F. So I have 5 degrees of freedom in the numerator because I have 5 differences. 600 is the denominator degrees of freedom, so that's where that came from. And my F is 4.7, and it says, yes, that's significant at a traditional alpha level. So the means are different from each other. Great. In R, I am using GLS from the NLME package because that's the only one I know of that doesn't insist you have a random intercept. Correlation equals null is how we set up an independent R matrix where we have equal residual variance along the diagonal and zeros in the off diagonal. And I'm asking for, in addition to just the usual summary of this output, I'm asking for minus 2 log likelihood to be printed, as well as residual variance because it's not actually printed by default. So I had to go into the bowels of the object and find it. So the first thing then, log likelihood, that's what you're going to put into the homework system when you start doing that for your models. And R is parameterized the same way as Stata in that it has the session, the first group is the reference, and then the dummy codes tell you about each other group relative to that one, so occasions in this case. The output looks exactly the same. Starting probably in the next example, I'm not going to show Stata in R for everything. Like I'll do one per model and switch back and forth. The only thing that's different with respect to the fixed effects, I want to point out, the intercept is first according to R and everywhere else in the world, and Stata always puts it last, and that drives me nuts. But I can't fix it. I tried. Anyone know how to fix it? No? Yeah, I looked for it and I just, nope, it's last. So the middle of the rows will be organized the same, but where the first one is at the bottom. Here is the total residual variation that I had to ask for to be printed separately. I'm then using something called EM means That is from a package. No one cares about the intercept. That is incorrect. The intercept is the "you are here" sign of your data. If you don't know where you are, you don't know where you're going. The intercept matters to me. Just ask the other class. I'm making them center already. We're doing simple linear regression and I'm making them center their predictor. So EM means does what you would think. It gives the means here, so it wants to know from what model you would like the means. RefGrid is an odd way to put that, but that's essentially what it means. I'd like pairwise differences by session. Adjust equals none is where you can change what kind of alpha protection you want to have if you need it. And then ANOVA, which actually means ANOVA here. So we get the means for each occasion computed the same way as above, and then all of the mean differences using denominator degrees of freedom with residual. So all the same stuff. And then here is the F-test I asked for last. Same agrees with R. So this is what the model says the model for the variance looks like. It wouldn't, neither software package would let me print this, but I got it out of SAS instead. So this model says the same amount of residual variance is left after adjusting for mean differences at each occasion, and there's no covariance whatsoever. That's our jumping off point for something better. So something better than repeated measures. How many kinds of repeated measures ANOVA are there? 1 or 2? 2. Yeah, I didn't know that. I learned that much later. This is the univariate kind, and what most people think about when they say repeated measures ANOVA. This is the version that comes to mind. It is indeed a model. So we are changing the structure of our R matrix, the variances and covariances left over after adjusting for mean differences, to exchangeable. Everything else, and now it's letting me use Satterthwaite degrees of freedom. That is a method of computing denominator degrees of freedom specifically. We'll talk more about that later. And I have the exact same set of mean differences as before, but the standard error part has changed. So note that the intercept has a different standard error than the others, and it has a different degrees of freedom. Because this model has a random intercept in it, that's what exchangeable means. We're building, this is U plus E. Because the model has a random intercept in it, the intercept, the fixed intercept, is treated as a level 2 parameter. So it has both between person variance and within person variance contributing to its standard error, whereas the others only have within person variance. So the mean differences are level 1 things, the fixed intercept is a level 2 thing, and the degrees of freedom operate similarly. In general, with the Satterthwaite method, degrees of freedom for level 2 things are going to look closer to what level 2 sample size is, and degrees of freedom for level 1 things is going to look closer to the total sample size minus level 2. So it's 500 because we're subtracting off 100 people. They do get a little bit weird though sometimes, and you will see decimals, for instance. So this is one thing that can differ across packages, is how they compute this, particularly for unbalanced data. The model for the variance then that is being built is out of these 2 parameters, and each package is going to give you a different version of them potentially. So this is called var-e. What do you think that would mean? The variance of the e's, right? Like, that's what it says? That's not what it means. Nope, they're just messing with you. It's total variance. It's U plus E. Even though that's the label is incorrect. So, cov-e, you would think is the covariance of the e's? Kinda. That is your random intercept variance, actually. That is the variance of the u's. So you have to do some math to figure out what the implied E variance would be. The good news is that Stata will print the pattern for these. It's doing it in scientific notation because the numbers are so big. But you can see this 2.4e on the diagonal. That's the same number all the way down. That means we're assuming the variance is constant over time. But this time, rather than having zeros in the off diagonal, we have something in the off diagonal. We have our random intercept variance. So this model says, yes, the occasions from the same person are correlated, but they're correlated the same way over time. So the model says that your performance at session 1 is just as related to your performance at session 2 as it is session 6. May not be the case, but that's what the model says. Here is the corresponding correlation matrix. I call this our core because I'm following the way that SAS names things. And this is our constant correlation across time. And that constant correlation has a special name. Do you remember? Starts with an I. ICC, yes, intra-class correlation. That's what this thing is. Software will compute it for you, but how you ask for it depends on how your model is specified. In this case, we are still using just one variance-covariance matrix for all of the residuals across time. So it's going to be in that. It will show up differently when we switch to a different version of the same model in which we have multiple matrices at work. So 0.86, is that high for an ICC? Yeah, what's the highest an ICC can be when it's computed this way? 1. So practically speaking, there is a very strong correlation of occasions from the same person. That's one way we can say it. I can also talk about it as a proportion. I'll make this a finger question, okay, folks? Is this 86% of level 1 or level 2? Got some votes for 2, that's it. Yep, the numerator is how much of the total variance is due to the level 2 random intercept or between person mean differences. That's how you can think about it. So most of it, 86% of the total variation in response time, according to this model, is because some people are better at this than others, the end. Only 14% is due to change that occurred over time as a function of practice and exposure. Here's my means. Here's my standard errors. They're still all the same because the model says the total variance is the same over time. And then here are all the mean differences. They all have the same standard error because, again, total variance doesn't change over time. Okay, 1 o'clock. How are we doing so far, folks? One thumb? Some thumbs? Any questions or things that you want to dwell on? No, we're good so far? So in terms of inference, our F before was 4, and now it's 32. Our effect got a whole lot stronger. That is because this model partitions variability. 86% between, 14% within. The tests of the mean differences are within. So essentially, we just canceled out 86% of the variance from our tests by holding each person as their own control, as I was taught. So by partitioning this, we end up with a stronger result, so to speak. But is it accurate? So we have 2 different versions of this solution so far. This is where what we talked about at the end of class is going to come in handy. How do we decide which model we like better? 3-word phrase. First word starts with an L. Second word starts with an R. Yeah, LRT. Yes, it is. What's that stand for? Bonus points. You can tell me that.
Likelihood ratio.
Yeah, likelihood ratio test. And because we're working with log likelihoods rather than dividing, we're going to subtract. And Stata has a built-in routine to do this. So for each model, I have a command that saves the results to Stata's internal memory. The name of the model here is the object that I'm saving is, I called it fit UWP. So testing fit in the univariate within person version of the model. And then LR test. Can you guess what that does? Yeah, it does the test for you. How nice. And it says assumption fit B nested in this one. So fit B was the first model. Yes, it is nested. They differ by how many parameters? The between person version that we started with that had no covariance versus the univariate version of repeated measures, how many parameters did we add? Just the one variance. Uncoincidentally, that's why the chi-square, that's what it's trying to tell you there, and the number in parentheses is the degrees of freedom. So we added one thing. This is treating this as a standard chi-square rather than the mixture chi-square that it probably should be. We'll talk more about that later, but a test statistic, this number right here, is a chi-square. That's how we treat it. And a chi-square of 800 on 1 degree of freedom is decidedly significant. We don't even need to worry about the mixture stuff. So this is a significance test that tells us what? Significant means what in this context? I see people typing. Significantly different, yeah, always, but which is better? Second model is better, yeah. So the way that we would talk about this, if we're adding things, is that what we added significantly helped. We have improved model fit, we've made the data taller by adding this additional parameter. If I want to talk about it the other way, I would say the first model fit worse. By taking away that parameter, we did damage, significantly worse. And what if reviewer 3 wants an effect size for the significance test because they don't like p-values? Is there anything in my output that might be useful for that? Question, so univariate within person or between person is better? Univariate within person is better. The model that has more parameters had a significantly taller height according to their log likelihood, significantly less shorter. Question, ICC and effect size, since it is a correlation, ding, 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 that's it. The interclass correlation is the corresponding effect size for this hypothesis test. So you can have non-significant results due to low power. You'd still want to think about effect size. The rules have not changed in that regard. So is 0.86 different than 0 is what this hypothesis test is asking. Is that correlation different? Decidedly different. And because the correlation technically could be negative, that's why it's not using the mixture chi-square. It's treating it as if doesn't have a boundary in this way of specifying the model. All right, R folks, I haven't forgotten about you. Here is the part that we change. All of that means exchangeable. And person ID is the ID variable that tells it which rows are supposed to be treated as together as a level 2 unit. So I have my -2 log likelihood from the model, AIC and BIC. AIC and BIC, do we want these to be big or little? Little. They start with -2 log likelihood as their core ingredient, so these are always in smaller is better form. And it gives me this thing, rho. Okay, I'd call that R, but whatever. It's the interclass correlation. And then it gives me the fixed effects. So these are exactly as what we saw above. And I figured out how to get it to print the model implied matrices as well. So there's a function called getVarCov that does just that. So what this is the marginal variance covariance matrix of the residuals. And I'm saying that deliberately, like this is all of it. Later on, we're going to start breaking it into pieces and different matrices to do different things, but right now it's all together. So this is all the reasons why people still differ from each other at each occasion after adjusting for which occasion it is. That's the only thing that's in the model. And this has a pattern of equal variance on the diagonal, equal covariance on the off diagonal, and then the correlation version I extracted from this piece of code right here is down below it. This pattern of equal variance and equal covariance over time has a special name. 2-word phrase. First word starts with C. What is that one? Cheers. Two-word phrase that means equal variance, equal covariance. Compound symmetry, ding, ding, ding. That's what it's called in SAS, in fact. That is what this pattern is called. EM means, again, to get the model implied means, and then ANOVA to get the mean differences. So the same information. That part, all of the means and mean differences are the same. It's the inference about them that has changed. So we have new standard errors this time. That's what makes this different from the other model. There's my F-test, and here's my likelihood ratio test. Now this is done with ANOVA. That has nothing to do with analysis of variance. ANOVA does model comparisons and analysis of variance stuff. It's very badly named. The order of the model comparisons here has to be the model that has more parameters first and then fewer second. I believe that is backwards from Stata, memory serves. Nope, it's the same. Stata is more and then fewer. So order does matter. And so it spits out the number of degrees of freedom, AIC and BIC, log likelihood, and then here's my likelihood ratio test result, same as before. Okay, this is not so bad, right? Now, this is a better model. We decided that, right? Likelihood ratio test says a correlation of 0.86 is not 0. Is it good enough? In balanced data, we have a way to examine that. In unbalanced data, we really don't. So in this case, we can answer the question, is it enough? Well, there's one more that is the answer key. Multivariate approach to repeated measures ANOVA. Do you remember what pattern that one is? It's not independent. It's not exchangeable. It is one other new vocabulary word, unstructured. Yes. So the same idea of saturated for the model for the means with respect to time, where we filled it up as much as it can be. We have 6 terms for 6 means. Unstructured is a word that means the same thing in the model for the variance. So how many parameters do we need to estimate for an unstructured model? A lot. There's a formula. Number of occasions times n plus 1. So that's 6 times 7 is 42, divided by 2 is 21. A lot. So that means we need at least 21 people. But we know that because they're not trying to recreate a pattern, we're just saying what the pattern is. We know that this is the best fitting model in terms of height that you can have. So unstructured is the key for that in Stata. Everything else is the same. And all of this is what it takes to do this in GLS and R. There is no way I would have figured this out on my own. Thank you, Jonathan. I rated his course materials to figure out how to do this. Yeah, so correlation equals CORSIM means all the possible correlations, and then weights equals var indent. Heterogeneous variances by time. That's what that means. Ugh. And we have -2 log likelihood and then our summary here. Now the way that this output is structured is unnecessarily confusing. Stata's is much more straightforward, so I didn't print that one. I don't think. No, I don't think I did. Yeah. So it gives me the correlation structure right here, which is helpful. And then it gives this thing, which the first time I saw that I was like, what is this? Because none of the numbers matched across what it was in SAS or Stata, which is usually how I know what things mean when I'm learning R stuff. These are multipliers. So what it's going to do is I've tried to articulate here in the text box here. What is given is each session's multiplier of the residual standard error. So these are in standard deviation units, not variance units. And so you would have 1 is kind of like the reference in this case. So I have 0.92 times the standard deviation of 1 gives me the result in terms of what it would be in standard deviation. So this piece of output that comes much later is what you need to understand what these numbers are trying to do. So this is helpful if you want to think about variance as a relative thing. like relative to 1, what is happening to the variance over time? It's shrinking. These are standard deviations, but same idea. It is not helpful if you want to get to what the actual model implied variance would be. So we have, these are the standard deviations that function implies. This is the one for the first occasion. And so I asked for extra output to put it in matrices so it would be easier to read. So things have changed. Let's look at the fixed effects. What do you notice that's different now relative to our previous models in terms of the pattern of these hypothesis tests? Did the estimates change? They did not. They're going to be the same the whole time. Standard errors changed. They're no longer the same. They are custom. They're based on however much variance was at each occasion that the two occasions are being the mean difference for. They're all still significant, but I'm pointing out the change here. We can ask for predicted means. Later on, I'll do that. This is the model implied variance covariance matrix. So we have total variance on the diagonal, and we have covariance on the off diagonal. So if you look at the pattern of what is happening here, the variance is shrinking over time, just like we saw in the observed data. So this is our best estimate of what the variance would be at each occasion. The data are complete, so that it's going to match the observed data in this case. And covariances are also appearing to be shrinking over time, but it's hard to judge that because covariance is a function of variance. Covariances have to be different if variances are different, so that's where the correlation version of this is a little more helpful. And it looks like there's a strong correlation over time, but it's not the same. So let me zoom in here and see the pattern. For instance, times 1 and 2 are correlated 0.84. That starts to drop off a little bit, but not much. Times 5 and 6 are highly correlated, but you can kind of see a pattern of decreasing correlation over time, but not much decrease, but it is a little bit heterogeneous. In terms of the model implied means, I got those out of EM means here, and so their standard errors are different because this model says the variance is different at each occasion, and all possible mean differences as well. Now our F value is 16, not 32, because we can't easily say how much is between versus within. That's not how this model is structured. It's more complex than that. Is this a better model? Survey says likelihood ratio test of 123. So yes. Unstructured fits significantly better. That means we should probably trust its results more in terms of the mean difference comparisons. All right. That's not so bad, right? So can I tell a story? I had two stories, actually. Why am I covering repeated measures ANOVA in a class on longitudinal models? Because I want you to understand what things are the same and what things are not the same. Okay. So I've been teaching, like, this is the first thing I ever started teaching. I've been doing this for like 20 years, probably, actually a little more than that. Yeah, about 20 years now. And a long time ago, I had a student who was very interested in bringing longitudinal multi-level models to their field and was really gung-ho about it. And he's writing a paper using those methods, and he wanted some feedback on it. So I took a look at it. And his paper was essentially like, all you dummies are using ANOVA, and you need to get with the program and do some mixed modeling. Multi-level is cool, and look at this. And he had 4 occasions, and he fit a saturated means model. And he ended up, actually, no, that's not relevant. He had a means model that was essentially saturated. And he tried to fit random slopes, and they were not significant. So he stuck with the random intercept and then went about his discussion section interpreting everything. So he had essentially saturated means a random intercept. Does he have a leg to stand on in telling everyone else that they're dummies for using ANOVA? Nope. I'm like, dude, it is ANOVA. That is an ANOVA model. You did it with REML estimation to avoid listwise deletion. You get to keep whatever data you do have, but you can't be all, you guys should do it this way. Like, it's the same thing. Okay, so that's story number one. Story number two. Different student, same university, had a intervention design where they had very few people. So they started out with like 30 people and they had 3 sessions, and by the end of it, they were down to 15. One of the things that they wanted to look at was they called it, like, I think, process data. So this is like a therapy setting, and so they're collecting things like how much of their homework did they do at this occasion, or how do they feel at this occasion, like so time varying information about how their process is going. So in order to help this student with the missing data and to be able to look at time varying predictors, I coached her through this multi-level modeling process. And she ended up with a model that had saturated means and a random intercept. And she didn't have much power for anything else. And it turned out none of her time varying predictors were significant. I'm like, okay, well, I'm not surprised by that. You have 3 occasions per person and you have like 30 people. That's not a lot of data. Well, her advisor knew better. They didn't like that answer that nothing was significant in their data because it was his study. So after many, many conversations with the student and trying to help her, she came back one day and said, he thinks that I don't have the data for this really fancy approach, and he wants to see what would happen if we did a repeated measures ANOVA. He was distrustful that I was trying to do too much. So I ask you this: saturated means, random intercept, what did I do? I did an ANOVA! But why didn't I call it that? Because if I did a traditional ANOVA, what would happen to her sample size? 15, listwise deletion. So you think your power is bad now with 30? At least you had 30 at one occasion. You would have to do listwise deletion. And that is not just a bad thing for power, that's a bad thing in terms of like who is left, right? If you think about this sample as trying to generalize to some population, are the people who stuck it out the whole time like random? No, there's probably meaningful differences between the people who stuck it out and the people who didn't, and those differences are going to be important to the story. So it's bad from an inference perspective, it's bad from a power perspective. Also, in her SPSS repeated measures ANOVA box, there was no place to put time varying predictors, so she couldn't even have answered the questions that she wanted to do either. So that's why I'm making a point about this. These models are indeed special cases of what I would call multi-level analyses. But the reason that these are endpoints, essentially, let's put it that way. Compound symmetry is one endpoint, unstructured is another, and we're going to have a slide that shows that in just a bit. That is 2 options out of many, many. So the benefit really is not these models per se, even though it does solve the listwise deletion problem. The benefit is that you have more choices in the middle. Because if you think about this is like all or nothing, right? Compound symmetry, all the correlations are the same, all the variances are the same. Unstructured, everything gets to be what it wants. Well, what if some of them want to be the same and not others, right? What if they're not the same in a pattern that we can anticipate with some kind of function? That's where we're heading. More choices in terms of what the patterns could be. ANOVA gives you these 2 only. All right. I had one more story. Oh, I know. I have a 3rd story. It's on the same topic. I helped publish a paper that once had 8 people as level 2. That's the smallest sample size. I have one with 9 too, also. 8 people. Not advised, but that's the data they had. This was a longitudinal class project. So, unsurprisingly, we ended up with just a random intercept in that model as well. No random slopes. And she had a quadratic function. So I think there were 7 or 8 occasions, maybe something like that. And it was like a bendy line. And no evidence for heterogeneity because there's only 8. And reviewer 3 was like, you can't run a mixed model on 8 people. Are you kidding me? I'm like, well, I just did. You need to do an ANOVA instead. Sir, it is an ANOVA. But I didn't have complete data, and I would have had to drop even more cases had I done it that way. So it is true that you are not going to get good estimates back of anything with 8 people, but it's not better if you called an ANOVA. There. I think that's all my stories for now. All right. How about, let's see here. We have lecture 4 to do. Do you want to save that for next time? Since it's like 1:23. You want to keep going? Yeah. Oh, they're smiling. Yeah, I'd like to save it for next time, please. We're actually a little ahead of schedule in terms of what I planned, so I'm down with that. So how about I let you go a few minutes early? You can go enjoy the lovely weather while we still have it. And please do your first formative assessment. And then we'll talk about it on Tuesday. How's that? All right. Thanks for Zooming with me. Let me know if you need anything. Bye for now.